So this integer factorization problem has a very well-known vulnerability to quantum attack. And the algorithm used with this quantum attack is called Shor's algorithm. Shor's algorithm recasts the integer factorization problem into a different problem called the order finding problem. And this is shown in the first equation on the left. So order finding is the problem where we're given a number a, which shares no factors with n, and we want to exponentiate it with a number r, and we want to choose r such that modulo n, this exponentiation equals 1. So if we do a little bit of algebra here, we can see that we can create a factorization that is related to our number n. And in fact, if we could find this order r, we could in fact, this factorization gives us non-trivial factors of our number n, and we can use an efficient algorithm called Euclid's algorithm to find the greatest common divisor of these factors that divide into n, and therefore we can find the factors themselves, p and q. The only question then is, how do we find this order r? So before we go into Shor's algorithm, the way we do this with a quantum algorithm, I want to give a little bit of intuition for what we're trying to do. So I've taken a simple case here, time series, constructed of computing a modular exponentiation, where my a value is 3 and my n value is 35. So this corresponds to the value n equals 35. So we want to find the factors of 35. This is a very trivial case, but it illustrates kind of the point of what we're doing. So our constraint, our order finding problem, is to find the index k such that this y value is 1. So, that's what we're finding, a to the k mod n equals 1. So if we plot out this sequence, we see that it's chaotic. It has sort of a quasi-periodic regime in the beginning and sort of devolves into a more chaotic regime afterwards. But the solution to our problem, where this value, the value y is 1, I'm showing it in the red circle here in the left-hand diagram. So if we can find this index k, this k is our r, our order. And so in this case, you can look at it a few different ways. We can visually see this. If you could zoom in, you would see that the y value is 1. In this particular case, we have a periodic regime that can compute FFTs and autocorrelation functions. All these kind of verify a period here. Now, in general, we don't necessarily have any guarantee of any particular structure here. We just need to find this one value associated with the red circle here. So once we find that r, we can plug it back into our formulas, and we see that we can compute our greatest common divisors, and we get the factors 7 and 5. So how do we do this in a quantum way using Shor's algorithm? There's a little bit of detail here. I'll try to just hit the high points, but in the quantum algorithm, it uses a method called quantum phase estimation, which is a problem that's sort of related to like a linear algebra type problem, where we have a unitary operator, which is a matrix. We have an eigenvector. We want to find its eigenvalue. But in this case, what we do, we can use quantum phase estimation to do this order finding if we choose a unitary that's very specific. So this is shown in the upper left. So we choose a unitary such that when it operates on the ket vector k, it multiplies this state by the number a mod n over a certain range of k. And then and so we have a circuit that we can see that leverages these unitary operations as controlled through bits in the index register, which is our top register here. As this index register is in superposition, values in that superposition control these unitary operations. And the net effect is that in the lower register, these lower qubits in register 2, we are computing this modular exponentiation function, except all of those values exist in superposition. So this is on the right-hand side of showing the algorithm itself, step 3. This lower register is the ket state on the right. We're computing this a to the k mod n function. Now, implicitly, we can rewrite this function. And by the way, this algorithm is taken directly from Nielsen and Chang with a slight notation change to be consistent with my diagram to the left. But essentially what we can do is rewrite this, the ket state associated with the lower register, which encompasses our modular exponentiation function. We can rewrite this in terms of the eigenvectors of our operator. And then what we see in this, I've highlighted in the red box here, what looks like a quantum Fourier transform of a ket state that is related to the one that we want. It's a ket state that approximates a scaling factor divided by the order to some number of bits of precision. So this looks like a quantum Fourier transform. So essentially what we've done, and this just implicitly happened due to our action of this of our unitary here, and this is the state of the first register. So since this is an implicit quantum Fourier transform, we need to do an inverse transform here. And by doing this inverse transform, we get a ket state that is an approximation of to the number of bits of precision that we have available, an approximation of a number that's very related to our order R. It's a scaling factor divided by R. And then this, after measuring this, this concludes the quantum part of the algorithm. And then there's some post-processing steps that can derive the order R from this other number that we measured. So this is Shor's algorithm, and it operates with order 1 success probability with order 1 operations. So very efficient.